Now that we've covered syslog and logrotate, and of course we'll revert to both as well as other things throughout our studies as time progresses and more data are collected, let's spend some time covering common networking utilities. Now we know that Linux is all about networking, and that means it includes tens if not hundreds of networking utilities. Utilities that allow you to access the wealth of protocols that are freely available. But of course, the primary emphasis is placed on TCP/IP, including IP version 4 as well as IPv6. So prior to getting into the differences between v4 and v6 and how they're implemented on Red Hat Enterprise Linux, let's warm you up to some utilities that are very helpful. So we'll label this section Common Network Utilities. And these are very common utilities, and again, there are tens if not hundreds of utilities. So by no means are we attempting to cover them all, but just some key tools that can help you to troubleshoot and diagnose network connectivity issues in your environment. So features includes useful for basic troubleshooting. So with that said, let's begin with an age-old utility, ping. Ping is really an acronym, although it's often referred to in the lowercase for Packet Internet Groper. So it gropes the target hosts by sending ICMP echo requests and expecting ICMP echo replies. So features ability to communicate with hosts using ICMP. A, ping sends ICMP echo requests, and B, ping expects to receive ICMP echo replies. So for each echo request singular sent to a target, ICMP echo reply singular is expected. But a series of ICMP echo requests are usually sent, such as 3, 4, or in the default configuration, an indefinite number of ICMP echo requests are sent to the target, and an indefinite number of replies are expected. At the end of it all, when you break the process, or after having specified a certain number of ICMP packets to send and receive, ping will produce a report which includes information related to the response received from the target. So we know what our network layout looks like. It includes a default gateway as well as other hosts on the network. And with that said, we can attempt to communicate with them. But just in case you've forgotten, let's just navigate to our document and bring it up on the screen as a talking point. So here's the classroom topology. This is the topology that we use for most of our classroom environments. And again, we're currently logged on to Linux CBT Serve 1, the Red Hat Enterprise box located at .1. And from that box, we can communicate with a multitude of boxes throughout our environment. So for example, we can ping the default gateway, which is always a test to see whether or not you have connectivity outside of your network. We can ping our local instance, our local system. We're currently logged on to this box here. So let's just zoom in a little bit, and again, we're on this box. We can ping ourselves, our neighbors, including the default gateway, including hosts in the DMZ, and possibly hosts on the internet if the firewall doesn't prevent us from doing so. So let's set up some basic tests. Ping some hosts and evaluate the output. So 1, we'll ping localhost and see how that behaves. Localhost translates to the loopback adapter's address, which is 127.0.0.1. In fact, the entire 127 subnet is reserved for the loopback adapter. So you can ping any IP address on this 127 network, and your local loopback adapter will return. So with that said, let's navigate to our shell and proceed to generating some ICMP echo requests. We'll just find this in the background here, and we'll find a window on our local system, not the remote system, and clear screen, reset the buffer. So by default, when you ping localhost, for example, it sends an indefinite number of 64-byte ICMP packets, and it expects an indefinite number of ICMP echo replies. Here we see the sequences, and they are listed in sequential order, with time to lives associated, or time to live values associated with each ICMP echo request, and the total amount of time the round trip packet took. You break this process by executing Control+C. At the end of it all, a total number of transmitted packets as well as received packets are returned. In addition, the percentage of the packet loss, which in this case is excellent, 0%, is returned. The total amount of time it took to send the 32 packets is just actually under 32 seconds that is, just under 31 seconds. It took 30,992 milliseconds, which is equivalent to just under 31 seconds to send 32 packets. Generally, ping sends packets in 1 second intervals. So when we run that again, you can count it. It's pretty much a second between each, and between each round trip. So when it gets a reply, that's roughly a full second. This may not always be the case when pinging hosts across your intranet or across the internet, but generally speaking, you can expect to receive a full response in under a second. Again, the full time is returned per interval. In this case, 22 packets were transmitted and received in under 21 seconds. More statistical information is provided at the end. The round trip time, the minimum, average, maximum, the maximum deviation. So the minimum out of this entire block of pings was, as you can see, 60/100ths of a second, or 0.061 of a second. The average was 68/100ths of a second, and that's the minimum round trip. The max was 74/100ths of a second, and the maximum deviation was, as you can see, 0.009, tenths, hundredths, thousandths, 9,000ths of a second. Now you may alter ping to send a specific number of ICMP requests. Let's scroll down. Again, this is a very simple tool, but it's a very important tool. By using the C option, lowercase, and n number of packets, such as 3, followed by the target will send 3 ICMP echo requests. So sends 3 ICMP echo requests, which means it expects 3 ICMP echo replies. So there we see the second and now the third, and we can take a look at the values. The minimum is indeed 65/100ths of a second, 0.065. The average, 0.67, that's the difference between the 3, or the average between the 3. The maximum is 0.069. So the values indeed make sense, and they correlate to the actual packet sent. Now when you ping localhost, the keyword localhost, name resolution takes place. We should just note that. Although it's slightly deviating, note, ping localhost performs name resolution using etc hosts. etc hosts stores static name to IP mappings. It is like having your local or your own DNS server for your own needs or for exclusive usage. A cat of etc hosts reveals a set number of hosts, including localhosts. Localhost is always included in the hosts file by default, by virtue of installing the operating system, so that when you reference localhost using tools like ping or any other tool, SSH, LFTP, you name it, it really translates to the IP address 127.0.0.1 with the help of the etc hosts file. Now we also mentioned earlier that if you were to ping any other 127 address, the system would respond. Your local system, your local IP stack would respond. Let's try that out. We'll send 3 packets to 127.0.0.2. And again, it responds, which proves that the entire 127 subnet is bound to the local loopback interface. You can pick any address that you'd like on the 127 network, and your local IP stack will respond accordingly. Here's a random pick of .25, and our local stack has again responded. So 127 is a local network. Note 127.0.0.1 and the full subnet, the full /8, so 127.0.0.1 or 0.0.0/8 is fully reserved to the loopback adapter of all IPv4 hosts, regardless of operating system, whether Windows, Linux, FreeBSD, Solaris, you name it. So long as it conforms to IP version 4 specifications, you'll be able to communicate with any 127 network, and you're really communicating with a local network card. So what does that mean with respect to this graphic? Well, we're currently connected to this Red Hat Enterprise 5 box. This is where we're doing most of our work, and from here we connect to other systems, such as the VMware instance running on our other server, this SUSE Enterprise 10 box, which has a Red Hat instance. When you ping your loopback adapter using 127.0.0.1, you're really pinging internally to this box. You're not generating traffic out onto the network, to the first switch, up through the GBIC, to the second switch. None of that takes place. You're in fact pinging the local system's loopback adapter, and it's kept local, and it's designed to be kept local. So how about pinging remote systems? Well, that's quite easy. We'll ping sending 3 packets to a remote system's IP address, 192.168.75.199, which is the Linux CBT Serve 4 box, which happens to be a VMware instance of Red Hat Enterprise 5. Let's give this a try. We'll clear screen. By the way, you don't need to be root to run ping. You can do so easily as a non-privileged user. And again, we see traffic information. However, the traffic information should be lengthier, longer, taking more time, as now the traffic has indeed traversed the networking topology. In this case, we pinged from our local system up through the 100 megabit link to the switch, up through the GBIC to the other switch, over to the SUSE Enterprise 10 box's VMware instance. That's this SUSE Enterprise 10 box's VMware instance. So there's a little bit of traveling, which explains the differences we see in time. Notice that in the case of the first ICMP echo request and reply, we see the time as 3.68 milliseconds, as instead of fractions of a millisecond. We see that for the second ping, it was a fraction of a millisecond, because usually after you've communicated or set up communications with a host using ICMP, TCP, UDP, any protocol, subsequent communication streams tend to be quicker. The setup stream, the first packet, tends to take a longer time, but once the host is up and running and responding, communications speed up. The third, although faster than the first, was slower than the second, but still fast in the overall scheme of things. And then we get the fact that we lost no information, and it took just under 2 seconds to send 3 packets. Here's the round trip timing for the minimum, the average, as well as the maximum and the deviation. So we have a deviation of just over 1 full second. Makes perfect sense. It took us 3.68 milliseconds